LearningMeasure.tv, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 42, Life, the Universe, and Radiometry.
Hello, I'm David Archer. I'm the owner of LearningMeasure.com. LearningMeasure.com is a subscription-based training website associated with the podcast. When registering with LearningMeasure.com, one gets one free week, and then after that it's $5 a month or $60 a year for continued access to all the courses. I'd like to mention a new course has been added to the catalog, ESD 101, Introduction to ESD Predictive Measures. This was a course that one of you guys out there asked for. They thought it would be relevant to have a course on ESD control for those of you involved with measurements, because you may have to deal with that in your day-to-day measurement life. I'd also like to announce that there have been two books that we've published now, which are basically compilations of course material on the website that's been slightly expanded. These are first two parts of a 9-part series of books we're going to put together on topics on the website. The first one is Measurement Series Volume 1, titled Introduction to Measurement Concepts and Measurement Uncertainty. And the second one, Volume 2, is the SI Systems of Units. Now, when you buy these, each one of these comes with a free 3-month extension to your LearningMeasure.com student account, and the details are in the last chapter of both books on how you go about getting that extra 3 months. So you can say that it's like $15 off. You get an extra $15 worth of value out of that. Okay. It's been over a month since the last podcast, and we've been busy. We're trying to line up people to do interviews. We still are. I mean, I originally thought that I could do this with like every other episode being an interview, but I've been having trouble getting people to do that. The other thing is because of my work situation, I work in Las Vegas and in Los Angeles, and I do these podcasts in Las Vegas. So we've been in the process of looking at trying to build a second location to do the podcasts from in Los Angeles so we can do them more often. The other thing we did, we've put together a YouTube channel where we're going to hopefully start making short, like 10 minutes or less, follow the YouTube guidelines, videos on parts of topics. And we plan on putting them on there and then incorporating them into some of the online course content as well, just to let you know what we're trying to do here. Right, and we are always working on new courses. The ESD course is the first of two we're planning on doing for ESD. One on geometric dimensioning and tolerancing, radiometry, and photometry, all of which have been asked for by somebody out there. And so if you guys want us to put together a course on any particular topic, let us know, and we'll up the priority of developing that. One of the courses that's closest to being ready is the radiometry course. So we thought we'd take this episode and talk a little bit about radiometry and photometry. Now, radiometry basically is the study of measure of electromagnetic waves of any type, any frequency, whereas photometry basically is concerned with visible light. And when we say visible light, that implies the eye. So photometry is basically measurements that are related to the response of the human eye. Radiometry is more of an absolute measurement of electromagnetic quantities. But before we get that, we've got to talk a little bit about the concept of angle and solid angle. As you may know, let's say you lived in a two-dimensional world, flatland or whatever, and you were inside some circle, and you happen to be in the center looking out. And let's say there was some object out there. You could define the angle it subtends by taking a projection of the edges of the object onto a circle, and then if this arc length here is S and the radius is R, the angle that's subtended by the object theta equals S over R radians. Now, because you know that the perimeter of a circle, total distance around, C equals 2 pi r. The whole circle is C over r equals 2 pi. So there are 2 pi radians in a circle. So, but yeah, the concept is you see this projection, you project it onto a circle, you take this ratio and you got the angle. Just for reference, we also like to break circles into 360 degrees. So if you want to convert from radians to degrees, you would take it radians to degrees, you multiply by pi over 180, which is really 2 pi over 360, and then take the 2 out. And from degrees to radians, you multiply by, or sorry, I got this backwards. From radians to degrees, you times 180 divided by pi, and degrees to radians, you take pi over 180. Sorry, got that upside down for you. You would have figured that out. Okay. That's angle. Now, the generalization of that, this is a two-dimensional world, but we don't live in flatland. We live in a 3D space. So we then have to go to a concept called solid angle. Okay. So you think about it the same way. You think of a sphere, and you're at the center of a sphere, and you're looking in some direction, and there's some object out here. Again, you project the area of that object onto the surface of the sphere. Oops, well, I guess it goes maybe bigger, whatever that would be. And so you have this area here and this radius here. You define the solid angle omega subtended by what you're looking at as omega, solid angle, is the area over the radius squared. Okay? And that's called steradians. It's really unitless, but it's called steradians. So for planar angles, it's radians. For solid angle, it's steradians. The abbreviations for that is SR. Now, since the area of a sphere, the surface area of a sphere, A, equals 4 pi r squared, there are 4 pi 4 pi steradians over the whole sphere. So if you want to look at the whole visible sky, it's 4 pi steradians. You need that before we can talk about some of the quantities in radiometry. Projected area. Well, if you have some surface, let's make it a rectangle. This is where drawing gets hard. And you're looking at this object from, let's say, over here. So this is your direction, your line of sight. This is some area A. Well, and this is the normal to the surface. We'll call this N. There's an angle here between the normal of the surface, we'll call it theta. Now if you look in this direction, and you sort of project things back in this direction, sort of what you're seeing is a different area. Yeah, I'm not very good at drawing these things. So this is a different area, let's call it A. The projected area, the area of this looking in that direction. It turns out the small area is the big area times the cosine of the angle theta, the angle between the normal and the line of sight. I bought a prop to sort of explain it better. See this book? It looks like a square. As I rotate it away from the camera, it looks like it gets smaller. Well, let's sort of do it so it's in front of the whiteboard. That may be easier to see. You see a rectangle. As I sort of rotate it, what you see, the area you see on the screen gets smaller. And if it was perfectly flat, when I get it to horizontal, it disappears. So the area you see, projected area, depends on the angle between the normal and the angle of the line of sight. That's the concept of projected area. Okay, so now we have angle, solid angle, and projected area. We've talked before about the concepts of energy and power. In radiometry, you talk about radiant energy. Radiant energy that's usually use a symbol Q, capital Q, in radiometry to indicate radiant energy, which is the total energy emitted by some source. Power, time rate of change of energy. We've talked about that before. Power in radiometry gets the name radiant flux. It's interesting how different disciplines use different labels and symbols for the same quantities. So this is usually represented by a phi. This is measured in joules. This is measured in watts, which is a joule per second. Okay, so this is power. We know that the relationships between them, phi equals dq dt, the time rate of change of energy, or if you want to think small quantities, the change in energy over the change in time. Likewise, power is the integral of or energy is the integral the radiant energy is the integral of the radiant flux over time, or for a steady power, it's equal to Vt. If something's putting out a steady radiant flux or power. Now we can start talking about some of the fundamental quantities. We've already talked about two of them, the radiant energy Q, measured in joules, and the radiant flux. Let's talk about something called an isotropic radiator. You have an isotropic radiator. You have some sphere, and it radiates power equally in all directions. That's the definition of an isotropic radiator. So a sphere centered on an isotropic radiator, all the power that radiates from the isotropic radiator makes it to the sphere, and it's evenly distributed on the sphere. So since the area of the surface area of the sphere is 4 pi r squared, the power per unit area, we'll call that S for the time being, is going to be the power radiated, which we're going to use the symbol phi, because we're talking about radiometry now, divided by 4 pi r squared. Now, this is in RF and microwave fields, this would be called sometimes called the power density. In radiometry, the power per unit area incident on a surface is called the irradiance. So irradiance is the power per unit area incident on some surface. Okay, what can you do with that? Well, we know, let's say the sun, we've measured at the top of the atmosphere. They've measured the solar irradiance at the top of the atmosphere, and it turns out to be something like, hold on, I'm trying to get the number here, 1,400 watts per meter squared. Now, I should say in radiometry, in radio frequency tests, they usually use the letter S. In radiometry, they usually use the letter E. I don't know why. We'll just call it E, phi for 4 pi r squared. Well, the sun's at the Earth's atmosphere has a irradiance, the radiance of a surface on the outside the atmosphere of 1,400 watts per meter squared. Well, you know this. We know the radius to the sun, so you can figure out the total power radiated by the sun equals 4 pi r squared E. And if you do that calculation, you come out with, you might want to try it, you can do it, it's easy enough. You get roughly 3.8 times 10 to the 26th watts. The world's energy production at the current levels is 1.5 times 10 to the 13th watts. The sun puts out 13 orders of magnitudes more than that. So you think that that you could do that with the sun. On the Earth's surface, the solar irradiance is something like 500 watts per meter squared, something on that order. I've seen different references. That's the biggest number I saw. I've seen it down as low as 100 and high as 500. So if you think about that, most of the world's energy needs, or at least the United States energy needs, can be taken up by solar collectors in something like the area of the state of Nevada. So there is some useful things you can do with these concepts, like computing how much solar collecting area you need to completely power the United States. And if you're willing to use the state of Nevada for that, or an area equivalent to that, you can meet the United States energy needs with photovoltaic, with current technologies, with current efficiencies. Okay, let's keep going on with some of these concepts. Oh, right, go back to the isotropic radiator again. We figured out the irradiance of an isotropic radiator. The next thing is a quantity called, where are we going? Where are we going next? Oh, right. Radiant intensity. Radiant intensity is the power per unit steradian. Okay, well, there are 4 pi steradians for the isotropic radiator. You would have the, what's the symbol on that one? So the radiant intensity is d phi d omega, the radiant flux per unit steradian. So for an isotropic radiator, it's going to be phi over 4 pi. You can do the calculation for the sun or stars, so you can figure out what the radiant intensity is, and that's usually the symbol for that is usually I. It's one of the ones that makes sense, intensity I. If you're curious to figure out what the radiant intensity is measured from the solar power arguments, you can. It's a fairly easy thing to do. I'll let you do that. The Earth subtends 1.4 times 10 to the minus 8 steradians from the sun's point of view, and that can tell you how much the radiant intensity is, or you can just figure the total power divided by 4 pi. All right. Then finally, the next quantity of interest is something called radiance. Oh, before we do that, if you have some area A, one thing before that, A, and this area is radiating, okay, and if it radiates into that forward hemisphere at power phi over A, which is usually called F, is called the radiant excitance. Okay, it's power per unit area. So, but we also know this is radiated. The other one we talked about earlier, which is also power per unit area, E, is the irradiance. So radiant excitance, power per unit area radiated, irradiance, power per unit area received. Although there is also a definition where this also applies to things radiating. Well, the next thing is, well, the concept of radiance. Radiance. Radiance is the power radiated per unit steradian per unit projected area. So, oops, I used the wrong symbol for the last one. Radiance, radiance F equals, well, this word phi d a cosine theta, projected area, d omega, solid angle. So, a source of constant radiance would look like, it would have the same what they call brightness per unit area. Like in a video game, constant radiance sources, as you turn them, they would just keep the same color. They wouldn't have, you didn't have to make them brighter and dimmer on the screen. So this is basically the last thing, quantity associated with radiometry. Well, that's about it, what we're going to talk to about this episode. We're running out of time. Next week we'll continue on with after we have these basic concepts, how you might make some of the measurements associated with them. Okay. It's going to be a little bit bumpy for the next few months, I think, as we work out the details of what we're trying to do here. So we're going to try actually to get things out more often than we have in the past. We may actually do some shorter episodes and then use parts of them in some of our courses. That's kind of what we're planning on doing. So we're going to break up this episode into pieces as well and put it into the new course that we're working on, just to see how that works. Okay, as always, if you have any questions you'd like to ask, send us an email at questions@learningmeasure.tv. If you have a suggestion for a show, send us an email at suggestions@learningmeasure.tv. And if you have, if you're a vendor and you want to be on the podcast, send us an email at vendors@learningmeasure.tv. Oh, we really are trying. We've been doing a lot of phone calling. We're trying to get some interviews lined up. When I started this podcast, we were hoping we'd get some more interviews, and we're working hard on that. That's kind of what my goal is. I don't want to be the only one talking, but we'll see how that goes. If you have any idea that you might want to be on this podcast, let me know, and we'll get you out here. We're looking for people to do technical talks. There'll be a short interview followed by a technical talk, and then a short sales pitch if you want to. So yeah, I'm trying to get people on for that. Okay, well, that's it for this week. See you next time.